Hello everyone, we are Team Thunder, and for our final project we worked on F110. So for this project, we wanted to address the need for reliable path tracking and responsive control based on environmental factors like traffic control. Our goal was to develop a self-driving system that smoothly navigates the marked path while adhering to traffic controls. Our initially proposed additional feature was stopping at stop signs. As a stretch goal, we wanted to also respond appropriately to red and green lights. As a whole, we wanted to simulate real-life driving conditions with the F110 car. Here we've included a block diagram showing the conceptual flow of our algorithm. We start by acquiring data from the RealSense camera. Then there's two flows of processing. The first is the stop sign detection, which is done with OpenCV, which then controls the braking control logic. Next we have the path following pipeline, which starts with the lane detection, which is the color and gradient threshold adapted from MP1. And then we do PID error calculation and then create the PID control logic to control the steering angle. Then the steering control logic and braking control logic are sent together and published to the F110 car. Here we've included some behind-the-scenes footage of the processing happening on the F110 car because we couldn't side-by-side it due to processing power limitations on the Jitsin. Here we've included a short clip showing what's processing on the back end in the PID control. So the red dot shows where the lane is based on the detection from our color and gradient thresholds, and the purple dot is the center of the camera. We calculate the error between the purple and red dot to calculate the PID error, which is then converted from pixels to steering degrees, which is then fed to the F110 car. Here we've included some clips to show our stop sign and traffic light detection. So we use a color thresholding and a contouring function to draw the shapes of the stop signs and traffic lights. Then we use the area to see how close we are to it so we know when to stop and go. Okay, so here we have our final results video. So as we can see, the car is clearly following the marked path. There is a bit of squiggling on the straight line, but it's more or less adhering to the path perfectly. And we're at a speed of 0.5 meters per second. So here we can see it's making the turn pretty cleanly and maintaining the 0.5 meters per second speed. Now we have a stop sign coming up. So as we can see there, it stops within about a foot of the stop sign and gets started again. Every time it stops, there's a little jittering from the motor, so we just have to give it a little kick to get it started again. Now we have the red light. So the difference with the red light is that for the stop sign, it stops for 3 seconds exactly and starts, but for the red light, it doesn't start again until it sees the green light. So you can start to see it jitter and start moving by itself before we actually kick it, which means it started on its own. We just needed to get it going again, which is why we kicked it. And then again, it's back to following the marked path. Here we'll go over some of the challenges we faced during the development process.
One challenge we faced was having the correct stopping distance. Sometimes it would stop too late and the motor would kind of wind up and it would slightly go backwards. To fix this, we fixed our minimum area detection threshold. The next problem we faced was in steering. So after large turns, it would overcorrect and continue to turn in that same direction without returning to the marked path. To fix this, we continually adjusted our PID values until we found a solution that would quickly adjust after large turns.
So in conclusion, we were able to achieve all of the goals for our project, including following the marked path and adhering to traffic controls. Thanks so much for watching and for a great semester.